I'm Joseph Stranges, and I'm going to give a presentation on D-metal organometallic catalysts for St. John's University. So the catalysts we'll discuss today are going to surround the D block elements, which are the transitional metals listed here on the periodic table. Now, to begin our conversation, I want to introduce a structure. The image on the right is an organometallic complex of N-butyllithium. The 4 lithium atoms are in purple. They form a tetrahedron with 4 butyl groups attached to the faces, with carbon in black and hydrogen in white. And these can be constructed to have ligands attached to them. And by constructing suitable complexes and exposing them to reagents and treating them in certain ways, we can affect organic transformations. These catalysts, they promote polymerization, hydrogenation, hydroformylation, and cross-coupling reactions when used. And they're very beneficial for their high activity, selectivity, and tolerance to various functional groups. And while various coordination modes of hydrocarbon ligands were determined one after another, the industry really started to kick off with lots of research over the last few years, and it increased with discoveries of olefin polymerization catalysts that we could use in synthesizing alkene metathesis reactions. So in these reactions, alkene metathesis reactions are catalyzed by homogeneous organometallic complexes that allow control over production distribution. A key step in the reaction mechanism is the dissociation of the ligand from the metal center to allow the alkene to coordinate. And olefin is just the piece after the carbon-carbon double bond is cut. And the mechanism of alkene metathesis is related to pericyclic reactions like Diels-Alder's reactions, and it occurs through the concerted interaction of one molecule with another. So here we see that metallocyclobutane is a prominent intermediate that undergoes rearrangement to get the product we want. And these metathesis reactions create a wide variety of organic compounds, and the reaction is typically an equilibrium reaction. Neither the reactant nor the product is favored in this case. So the structure is produced like a ring opening metathesis polymerization, a cyclic diene metathesis polymerization. All will produce probably about half the product we want, unless we're using larger quantities to see more of this product. So these reactions are catalyzed by molybdenum aryl carbene complexes and ruthenium carbene complexes, which look just like these. Since pretty much the 1950s, when these newer catalysts have been introduced, and the development of the ruthenium compound came to light in 1992, and the molybdenum complex shown on the right came about just shortly before. But both of these catalysts gained the respective scientists the Nobel Peace Prize. And in the case of the ruthenium catalyst, better known as the Grubbs catalyst for the scientist who coined it, it is known that the dissociation of the PCY3 ligand from the ruthenium core is crucial in allowing the alkene molecule to coordinate prior metal cyclic butane formation, the intermediate we saw earlier. And this gave light to the identification of the second generation Grubbs catalyst, which just basically replaced one of the PCY3 ligands with bis metacyl N. NHC ligand. And it's active in the presence of a large number of different functional groups on substrates, which is a great benefit. On the right is one that Schrock developed. He developed tungsten and molybdenum complexes that were commercialized in the 90s. And these catalyses were synthesized not too long after to address stereochemical control because of these large, bulky groups. This is known as tacticity via stereochemical control, which is something that we'll bring up a little later. Another method is the hydrogenation of alkenes. An example of an alkene addition reaction is exactly what this process is. In a hydrogenation reaction, 2 hydrogen atoms are added across a double bond of an alkene, resulting in a saturated alkane. And it's thermodynamically favorable because the product is lower in energy than the reactant, releasing heat in that case. And the Wilkinson's catalyst is what's helping us out here. It's used widely in this method, and it's related to complex used at pressures of about standard normal conditions. And it's suitable for chiral ligands, which can lead to enantioselective hydrogenations. Enantioselective hydrogenations are obtained using chiral ligands with translation metal catalyses, which would form optically active products. And here we have the catalytic hydrogenation cycle with the Wilkinson's catalyst. So for the reaction to proceed, the alkane must be just the right size because steric hindrance won't allow the compound to be hydrogenated. Sterically crowded alkenes don't coordinate well, and the alkene forms a strong complex that doesn't react any further than that. So this cycle is used in a delicate sequence of reactions, and anything that might upset this flow may block the catalyst from forming correctly or alter the whole mechanism. The alkene to be hydrogenated must be prochiral, which means that it must have a structure that leads to some R or S chirality when complex to that metal. The complex is going to have 2 diasteric forms, both R and S. And the enantioselectivities are normally measured in terms of the enantiomeric excess, which is the percentage yield of the major product versus the minor. And an interesting detail of the process is that the diastereomer is leading to the major product in the R form. As you can see in the right, the reaction coordinate shows the larger peak for the green curve, showing R being the major isomer. The minor R isomer will be S. A next process is hydroformylation or oxosynthesis. This process is for the production of aldehydes from alkenes. It involves the addition of a carbon monoxide and hydrogen gas to an alkene. And the mechanism here is thought to involve a pre-equilibrium in which some carbonyl or some metal will combine with hydrogen at some high pressure. So the mechanism here involves the initial formulation of a metal complex and the coordination of the alkene so that we could insert the carbon dioxide and the hydrogen. So here, this is the catalytic cycle for the formation of alkenes using a cobalt carbonyl catalyst. It's in a series of steps. In A, there's the formation of the tetrayl carbonyl hydride cobalt intermediate. B shows the formation of the coordinativity of the unsaturated complex. Then moving on forward is the coordination of the alkene and formation of the alkyl complex. Then migratory insertion and formation of the acyl complex. And then last but not least, we get our aldehyde group, which represents our final product. Next is Wacker oxidation of alkenes. This is used to convert ethene into an ethanol by oxidizing alkene with oxygen. And it's the most successful system, uses a palladium catalyst to oxidize the alkene. It acts this way because it's the initiating oxidizer. It refers to a general transformation of a terminal or an undistributed alkene to a ketone through the palladium. The catalytic cycle for the palladium catalyzed oxidation is shown here in 5 steps. First is the oxidative addition when we introduce the palladium in its cationic state. Then we move on to the coordination of the alkene, where the palladium coordinates the alkene substrate. Then we have insertion. And then in 4, we get the deprotonation and production formation. This is where the alkyl complex is deprotonated, resulting in the loss of the halide ion, forming an inorganic product that attaches to the palladium. And then finally, we get the regeneration of palladium from neutral back to +2 in the presence of a reducing agent so that it could be used again. Next up, we have palladium catalyzes carbon-carbon bonds forming reactions. So these reactions proceed through 2 steps of oxidative addition and reductive elimination. And a number of palladium catalyzed coupling reactions are known. They all proceed through oxidative addition of reagents at the metal center, followed by reductive elimination of the 2 fragments. Here in the catalytic cycle, in an idealized cycle, we'll begin with oxidative addition. The reaction begins with the addition of the aryl halide. Then we move on to alkene coordination, insertion, beta hydride elimination, and reductive elimination, followed by the regeneration again of palladium. Then we move on to oligomerization and polymerization. Oligomerization process converts small molecules into larger molecules synthesized by smaller monomer units. And polymerization combines many monomer units to form a longer chain. Ethene can be oligomerized to linear alkenes by homogeneous catalysts with a nickel catalyst. And this is commonly known as the Ziegler-Natta catalyst. And here, the conversion of the long chain alkenes is happening in the shell-higher olefin process, better known as SHOP. This is a 3-step catalytic process developed in the conversion of ethene. So the steps involve oligomerization of the ethene to form short chains from up to 10 monomer units. And the Ziegler-Natta catalysts used here polymerize alpha olefins with high linearity and stereoselectivity, but the full details of this mechanism are still uncertain. But the Cossé-Arlman mechanism is a little bit more plausible. Here, the catalyst is prepared from TiCl4 and AlC2H5. So those two react to give TiCl3 mixed with the AlCl3. And then the solid ethylene molecule coordinates to the neighboring vacant site. In the propagation steps for the polymerization, the coordinated alkene undergoes a migratory insertion reaction, which opens up another neighboring vacancy, so the reaction can continue to the polymer chain and it will grow longer. So some catalysts remain in the polymer, but the process is efficient so that there aren't much that are present in the end. So these catalysts are pretty cool. They contain at least one metal that facilitates the chemical reactions, but they're very useful in some cases, especially when they're synthesized around their specific properties. We're able to classify types of them based on the metal involved and common catalysts depending on their oxidation states, like palladium. But they all operate through their own different mechanisms, so they all follow their own unique series of steps, and they offer highly selective and efficient reaction outcomes when used properly under their right conditions. Here are my references for this presentation, and thank you.